So I'm presenting Wasocaml. So compile OCaml to WebAssembly or Wasm, because well, it's neither an assembly nor for the web. And so that's Leo's work, my student, but well, he couldn't come here. You shouldn't let your students submit articles when you're not sure they could come. You will see me far too much in the next 2 days. And yeah. So why compiling to WebAssembly? Since, well, OCaml already has compiler to JavaScript, which works quite well. Because basically JavaScript has some problems when you compile to it, is that it's quite unpredictable in performances, and you generate gigantic JavaScript files that can take quite long to load. WebAssembly is a lot more compact, and basically has always the same performances, and you should expect that the performance difference between different runtimes is going to be a factor between one or another. So, well, and yeah, there are some places where you can't run JavaScript, or just better to run WebAssembly. So, as Andrès told you, the basic first version of WebAssembly had things in there, but basically only what you want to compile C-like languages. And if you wanted to compile OCaml, you had some restriction. And it was quite hard to communicate with the environment. So what does WebAssembly look like? Something like that if you look at the stack syntax. But Andrès lied to you, it's not a stack language. It's an expression language. It's just different encoding. And well, that's factorial in WebAssembly, nothing special. So it's fine to compile C, C++, Rust without any trouble. If you want something to do something quite naive, it's not going to take you long. It's mostly going to take you some time to implement the runtime, the libc for C, because well, WebAssembly has nothing for the rest of the world. It's just a language, not an environment. So if you want to compile your language, you generate naive WebAssemblies and you call binarian to handle whatever is specific to WebAssembly. And it does quite a good job at that. So just be naive, it's going to work. So, but if you want to compile CAML or SML or any garbage collected language, then that's going to be more troublesome because you need to keep tracks of your roots. And keeping tracks of roots, you can either do that into a shadow stack, or you can do some other tricks that are a bit more complex, but you can't inspect WebAssembly stack. It's completely opaque, and for good reasons. So, well, you have to do something, and then there's another problem because your garbage collector is your own garbage collector. If you run inside the browser has a different garbage collector. Pointers between two different garbage collectors is always a problem. And you're not going to be able to collect cycle between the both languages. So, so you want to do something else. In fact, in Wasm-2, there are external refs that helps a bit with something like that, but yeah, that's not completely the solution. So we want something that is, well, like WebAssembly, quite fast, that does not slow basic Wasm code, and can represent any garbage collected languages. So apparently CAML was kind of a good model. The memory model of CAML was quite a good model because it looks a lot like the actual values of CAML. So thanks, Andrès. That's quite helpful. But there is a bit more because, well, you want to efficiently access values, don't cast too much. So there is kind of a type system for the objects that you can allocate inside Wasm-GC. And it's a type system that allows you to go to upcast easily, but don't downcast naturally. But you can still downcast, and you can downcast quite effectively. So upcasts are completely free. They are just even implicit, but upcasts are supposed to be basically pointer equality or something like that. So it's supposed to be quite cheap. And in practice, you can look at that as kind of a structural typing discipline that is encoding into nominal typing if you do whatever you need to describe all your nominal types, all your potential structural types as nominal cases. So, well, where does that fit inside the OCaml compiler chain? So that's what the OCaml compiler look like. Not exactly, that's OCaml plus current development branch. So you start from the source, you compile to, you type check, parse, and then you forget the types here, which is basically an untyped lambda calculus. And then you can go to the bytecode, and then to bytecode to JavaScript with JS of OCaml. Or there is the old path of the compiler, or somewhat newer path, or the current development path that you will hear about from me. And you can compile to WebAssembly basically from there with Wasocaml, or maybe from there later, because currently what I'm presenting is kind of a prototype. So why did we choose that level? So basically everything before f lambda is a bit too high level and not very convenient for us, because WasmGC has functions, has blocks, values, and whatever, but don't have closures. And whatever is before f lambda don't has explicit as closure in the language. F lambda has explicit closures, so you can separate the construction of function and the construction of the actual closure. And the control flow is quite easy to translate to WebAssembly, which basically allows to build all the kind of control flow you want. It's kind of restricted, the control flows that you can build in Wasm, but you can just be naive and let Binarian take care of simplifying that for you. So the next version from the 2 is going to be basically the same thing. There is not going to be any more trouble. So some OCaml. That's the version in f lambda, some kind of printing of that. So if you look at it, you see that we explicitly allocate closures. And yeah, we project from closure, we have explicitly access to fields. So that's quite simple. We have explicit lets everywhere, no nested expression. Something that is quite simple to translate, that generates horrible WebAssembly when you just do that naively. And we do that naively, but we don't care. Binarian is here for us. So everything is represented as what is called an ecref type in WebAssembly. So that's just under any. So any is the level where you can represent any kind of values. Ec is any kind of value on which there is the equal operator, which is quite convenient because there is the physical equality function in OCaml. So we need that level. And we don't need anything that is at the any level, but not at the ec level. So quite convenient for us. So why don't we construct anything that is more precise than that? Well, the reason is that the OCaml type system is quite complex. We forget most of it when we go to the lambda language. It would be quite horrible to be able to reconstruct some interesting type for it. And OCaml programmers tend to be not so nice to the type system sometimes and use the magic function that destroys everything. So, well, we have to assume that the program is kind of well typed, but not too much. So, for the basic values, we use something that is a struct. And for small integers, we use int31ref, which is something that fits into a pointer or a standard value in WebAssembly, and which is also compatible to a structure. And int32, int64 are not compatible with those types, but that's something that that fits in any reference. So that's quite convenient, and we kind of pushed for that, and it was apparently not too much rejected. Otherwise, OCaml's arrays are represented as WebAssembly arrays quite naturally. So, something about the type representation. Yes, there is object magic that makes everything troublesome. But also, then when we access a field, we don't exactly know the type, the size of the field we access. We just know that when we access the field n of a value, then it has n+1 fields at least, but not much more. So that means that we need to use the subtyping chain that WebAssembly proposes if we want to represent things as struct. And then a block of size n, we could access any field lower than n. But then that means that when we do an access, we take an href, we cast to just the size that we want, and if it's the right size, if the type checker didn't complain when the OCaml program was compiled, that should be correct. And the cast is valid. But then we need to have compatibility between different sizes. So the subconstructor, I don't know if we can see, that tells that blocks of size 2 are effectively subtypes of block of size 1. So in fact, it's not exactly that type that we use. We add mutability to every field because, well, OCaml have letrex. You can't build recursive values without mutability, sadly. We have ideas for potential Wasm extension to change that, but that's going to be Leo's work to write the details. Also, that encoding is great, but there are stupid OCaml libraries, like OCaml emojis, which has basically one definition for each emoji, and that's a lot. OCaml modules are represented as blocks. And so you can imagine that those are quite long blocks. The problem is that the subtyping chain is quite long, and for good reason, there are limits to the length of subtyping chain, because there need to be something that represent inside the engine some structure of the subtyping chain. And if you have a gigantic subtyping chain, then finding something in that structure is going to take some space, and that's not some space that you want to waste in something like that. Especially that in practice, nobody wants to do something that large. So since we want in WebAssembly that everything has predictable performances, we want the cast to be basically always taking always the same time, having the same sequence of instructions, and not depend on the actual type. So you could encode something that would be logarithmic in the size of the types to actually check. That would be possible, but probably undesirable. And that's something that the user can encode itself. So it's probably a better idea to let the compilers that generate WebAssembly handle itself and do the logarithmic tree of the typing. But that's not what we do, because basically we're too lazy and we did a naive version. So we did implement the struct one. It blew immediately, basically, because the subtyping chain is of length something like 60 or maybe 100 now. Too small even for standard OCaml standard library modules. So the naive version is just to say, well, everything is an array. And you can store integers in arrays. So you store in href. So it's an array of href with everything shifted by 1 and the tag stored in the first position. It's not wonderful. We could do better, but that's clearly the simplest way to go. But I'm not even sure that it would be slower than the struct version. This has to be benchmarked, and well, before benchmark, you never actually know. And we don't have sufficiently precise benchmark right now to decide. So we might try the other solution at some point for real. So how do we encode closures? So closures are functions and fields that capture the environment. So basically, you just have fields for the function. Because functions are not compatible with the other reference values. You don't want to mix everything in there. So you have to pack them into structure. But it's okay into structure. You can have things that are different types and that are not compatible. And that's all. It works quite well. But if you want to do that, you need to be at an intermediate representation that do actually represent explicit closures. So compiling to that directly from something that is a lambda calculus is going to be a bit troublesome. You want to do the closure conversion before that. So in fact, it's a bit more tricky than that, because OCaml functions and closure have lots of funny things. So that's the actual encoding for the function of type at most 2 arguments, and with closures a function of 2 arguments that contain 1 field. So that one is the function of 1 argument, nothing really special. But we have the recursive definition of type, because WebAssembly allows the recursive definition of types. So the function knows the types of the environment. The environment knows the type of the function of 1 argument. And the thing is that the function of 1 argument in OCaml is the super type of every function. Because every function in OCaml can be applied to just 1 argument. So, and you don't know really from the type that it's the case. It can be completely dynamic. So you have to be able to cast any function to a function of 1 argument. And so when you apply an actual function of 1 argument, you just call that. But if that's something which has more than 1 argument, then you need to allocate intermediate functions. And well, that's some trouble, but it works quite well. We basically use exactly the same schema, the one that is used for the native OCaml compiler. And that's quite decent. So OCaml have exception. OCaml use a lot of exception. We use that for control flow, for everything. That's nice. And what's also nice is that there is another proposal in Wasm that proposed to add exception to Wasm. I think that we were not the main target for that originally. We don't have enough weight for something like that. It was C++ that was the main reason for that. We don't care. We are okay to just steal the proposal. So we basically just use that as is, and it basically allows to represent OCaml exception without any trouble. And I think other languages are not going to have problems with that. I've just heard that it's completely going to change soon. So maybe that's not going to be the case anymore. But I trust Andrès and others that's going to work. Yeah. So it was simple enough. So if it's simpler, then it's really simple. So alongside the actual development, Leo worked on small steps semantic of F lambda and something that is similar to for F lambda 2 to be able to prove things on the compilation. So it's the first semantic of something at that level in OCaml. Well, that's nice. And he has interpreter and stuff for that, and a compiler of the mini version to WasmGC, just to be able to try his own semantics against some semantic of WasmGC we'll see. We don't know exactly the details of that, so there are no proof right now of the actual compilation. We imagine some version, but well, the proof are going to have to evolve. But the proof is going to be probably quite simple, the actual proof, because the semantics of WasmGC is very similar to the semantics of a standard ML, so no problem. So if you want to try that, it's there. So there are 2 URLs for that. You can go see it wherever you want. But that's a prototype. If you really want to do something serious, right now it's a bit early. By the way, no actual browser can use that for real, so that must be experimental. So otherwise, that prototype, I think, was basically the first of a kind of real language, because that's just a prototype for WasmGC. So I think we kind of validated that validated the proposal for something that was not crafted after the fact. Andrès did write a functional language to test the proposal, but he could assume that, well, he designed it for the proposal, so you never know that if you can patch that into an actual compiler without destroying everything in there. We showed that in 31 ref is quite useful, and that was not obvious at that point that it was going to be kept. But you can't use that for real program right now, because we were too lazy to implement the full standard library, because, as I said, you don't have libc, so you have to do a lot of things to expose actual useful functions to your program in WebAssembly. So we do compile basically everything in OCaml except objects, but who cares? No, and in fact, it wouldn't be difficult. We just didn't do it. But we didn't do the standard library. We are going to steal the one from Wasm-GC from Jérôme Vouillon. And that will be a lot simpler than actually writing it. And yeah. So how does it perform? Because that's always the question when you have a new backend. So it performs quite well, given that everything is quite experimental. So if you do some classical micro benchmark, which are micro benchmarks, so you shouldn't trust the results. That's basically at worst kind of 2 times slower, and that's basically always the same factor compared to native code. So that's quite good. That basically achieves what was expected of WebAssembly, which is having predictable performances, which is absolutely not the case when you have JS of OCaml. You kind of have the same speed in JS of OCaml in best cases, but the worst cases can be very horrible. But as I said, exceptions were meant for C++, and apparently were not optimized like hell right now in V8. So And yeah. But we did hack a few things, just try to avoid the problem. And if we try to don't rely on exception, programs that do rely on exception in OCaml, so Knut Bendix, the preferred benchmark by Xavier Leroy. So usually he says that it performs basically the same as Coq, so it's a good idea to have that fast. Xavier is going to be happy. So it's a bit slower than the programs that don't rely on exception with the exception implementation, because your functions are going to need 2 arguments you need to check at the return of each function. But that's not horrible. We don't take an horrible slowdown. So either we wait for future proposal, or we push for future proposal on an exception for that to be faster, or we can just use that encoding. So otherwise, should we care about the cast? Probably not that much. We could optimize to remove as much as possible, but that's at most a 10% gain apparently. So V8 has a mod to try to segfault it, where you say casts don't exist. So it's quite cool because you can see the differences between the best case and what you actually have. And you know that right now it's like 10%. We don't really care about that level of difference. We could go a bit lower because I found that who has more information about types. But well, maybe we won't even do that. So otherwise, what happens when you have to interact with the rest of the world? So we will do what matters for the studlib. But if you want to run on the web, you can also use JS of OCaml FFI, because you can expose the JavaScript FFI as something that would be compatible for WebAssembly and calling the JavaScript through something that is a method call for JavaScript. That's some hackish thing, but that's possible, and that's probably to be quite slow at some point, but possible. Otherwise, you can hack things to get C compiled to WebAssembly and use that. We think that recently there were changes in C-Lang that allows to use the external ref. That's still unreleased, but it's probably going to be possible to just compile that, change a bit the header file that you use to compile your C, OCaml C code, and that's just going to work without too much trouble. Just changing a bit things because the field access is not going to be an L value anymore. And I think I should, yeah. So there are lots of different other options because apparently OCaml guys want to compile. And yeah.
Okay, thank you. If there's one quick question. Okay.
Yeah, first of all, awesome. Great.
No, it's on.
It's on? Ah, okay. Yeah, awesome. I have one question. So with it's unfortunate that the exceptions are so slow in V8 when you use them this way. I was wondering, do you really need to return, though, a flag with every call? Can't you just have a global flag that you set when an exception is thrown and check that?
Is that going to be any better? Because that's kind of going to go into a register compared to global access.
Might be worth trying. I don't know. I would expect that to have much less overhead. What would you think?
More return here, probably.
Okay. Yeah, just
yeah.
I was just wondering.
Okay, so let's thanks again.